Hello everyone, I am Srisha, a student at the Indian Institute of Technology, Madras. Today we are presenting a brief announcement, Automating and Mechanizing Cutoff Proofs for Parameterized Verification of Distributed Protocols. This paper is co-authored by me and my guide, Karthik Nagar. Parameterized verification of distributed protocols deals with verifying whether a given protocol meets its specification for all values of the parameter. The parameter of interest here is usually the number of nodes in the system. Cutoff-based approaches for parameterized verification depend on the following observation for a protocol. If the protocol violates its specification for some arbitrary value of the parameter, it is guaranteed to violate its specification for a parameter value less than or equal to k. K here is then called a cutoff for the protocol. Cutoff results are useful as they reduce the search space for verification. Once a cutoff k is established, exhaustive model checking in systems of size less than or equal to k decides the correctness for all values of the parameter. Most of the existing approaches for parameterized verification use some form of inductive invariants. Inductive invariants are a set of properties of the system that hold inductively at every step of the protocol. Furthermore, they must also be strong enough to imply the specification. This approach has resulted in many useful frameworks such as Ivy for specifying the protocol and the specification in one language. This has also resulted in techniques for fast and streamlined verification of complex protocols. Techniques have also been developed for automatically synthesizing inductive invariants. The cutoff-based approach has also been used successfully in the past. However, most of these works impose significant restrictions on either the class of specifications or the class of protocols. Additionally, some of these works also impose restrictions on the communication model. For example, the work by Jaber and colleagues deals with protocols that use consensus as a building block, and the work by Marik and co. considers protocols that have consensus-related specifications. We believe that cutoff-based approaches can have a broader range of applications. Coming to our contribution, we develop a methodology to automate and mechanize cutoff proofs for parameterized verification. We propose a principled strategy to synthesize this simulation relation from a direct mapping between nodes of an arbitrary size system and nodes of the cutoff system. We then encode the inductive correctness of the simulation relation as a first-order logic formula, thereby reducing it to the satisfiability problem. We further motivate a sufficient condition which relies on simulating up to the first violation. We have also tested our approach on a variety of protocols. We now demonstrate our approach on an example protocol. Consider the leader election protocol in a ring network. The ring can have an arbitrary number of nodes, each with unique IDs, and there is a total order on the IDs. The system state is defined by two relations, PND and leader. PND m, n holds if the message m is pending in the queue at node n, and leader n holds if n is the leader. The protocol proceeds by sending messages in one direction of the ring. This can be abstracted away into two actions, generate and handle message. In each step of the protocol, one of these two actions is fired non-deterministically and atomically. The specification for this protocol is given as a safety property, that is, there is at most one leader at all times. When the generate action is fired at a node n, the node n sends a message to its neighbor containing the ID n. The neighboring node then places this message in its pending queue. As an example of this action, consider the following 4-node system as per the protocol. The nodes NA, NB, NC and ND have IDs A, B, C and D. In the initial state, PND D, NA is false, and after firing the generate ND D, NA action, the node D sends a message with ID D to node A, which places the message in its pending queue. Consequently, in the final state, PND D, NA is true. The handle message action at a node determines what happens to a pending message in its queue. As an example, assume that the message m, which has to be one of the IDs, is pending at node A. This is a guard that has to be enforced before executing the handle message NA m, NB action. Depending on how m compares with A, the following cases can arise. If m is greater than A, then the message is forwarded to NA's neighbor NB. If m is equal to A, then the node A is elected as a leader, and if m is less than A, then the pending message is simply deleted from NA's pending queue. We show that the cutoff for this protocol is 2. Consider any arbitrary size system L in which a sequence of actions leads to two nodes LA and LB with IDs A and B being elected as leaders, which is a violation of the specification. We construct a cutoff instance of size 2 with nodes CA and CB with IDs A and B. The idea is to show that given a sequence of actions which lead to the election of LA and LB, there exists a sequence of actions which lead to the election of CA and CB. To do this, we first define a function sim which maps nodes of the system L to nodes of the cutoff system C. The intuition behind this function is that we want the node NC in C to maintain the state relevant to the safety violation for all nodes N of L which map to NC via this function sim. For our example protocol, we define sim such that all nodes in between LA and LB, including the node LB, are mapped to CB, and the rest of the nodes in L are mapped to CA. As an example, consider the following instantiation of an arbitrary size system L with 4 nodes and the cutoff system. As highlighted in the figure, the red nodes in L map to the red node in C, and the blue nodes in L map to the blue node in C. The simulation relation relates the state of node N in L to the state of the node sim N in C. It essentially enforces the intuition behind the sim function. That is, it ensures that the state components relevant to the violation in node N of L are present in sim N in C. Mathematically, this can be expressed as in an abstract formula as shown. The function omega in this formula is essentially a filter which removes the state components of N that are not relevant to the safety violation. For our example protocol, the abstract formula provided above takes the concrete form shown here. We can see from the formulation that the simulation relation preserves the violation. That is, if LA and LB are elected as leaders in L and the correctness of the simulation relation has been established inductively, then CA and CB are also elected as leaders in C. To enforce the simulation relation, we need to define a lock step. The lock step essentially defines what actions or action are to be taken in C for every action taken in L. Usually, the sim function provides the necessary transformation directly. That is, an action involving node N1 and N2 in L is translated to an action involving sim N1 and sim N2 in C. However, from our experience, certain corner cases can arise. For some actions which involve the state components of L that cannot be simulated in C, we would have to perform no action in C. This represents a stuttering step in L where L transitions according to the provided action, but C does not actually change its state. Similarly, we could have one action in L needing to be translated to multiple actions in C. This is sometimes needed to maintain the simulation relation. All this complexity can be abstracted into a single function tau, that is, an action A in L is translated to action tau A in C. For the leader election protocol, the definition of the abstract function tau takes the concrete form shown in the slide. Note that apart from the actions for which tau is defined on this slide, we have the symmetric versions with A and B interchanged, which also hold. The rest of the actions in L which are not, for which tau is not defined here, are stuttering steps in C. The simulation relation must hold at every step as the two systems L and C progress according to the lock step. To show this, we propose a tool. The inputs to the tool are the protocol description, the sim function along with the cutoff instance itself, and the two functions omega and tau as described earlier. We need to show that the simulation relation holds inductively as L and C progress according to the lock step. To do this, we synthesize a first order logic formula which, if shown to be unsatisfiable, implies the inductive nature of the simulation relation. In words, the formula essentially does the following. Consider an initial state of L and C that obeys the simulation relation. Perform one action A on L. Note that here we can choose any one of the actions A defined in the protocol description. We then perform the corresponding action tau of A on C. Finally, we assert that the final states of L and C after this one step do not obey the simulation relation. We further observe that it is sufficient to simulate only up to the first violation of the protocol, as once the first violation occurs, the specification is broken. Therefore, we can actually assume that the safety property holds in the initial state of the formula above. This is equivalent to appending the specification conditions on the initial states of L and C to the above formula. Finally, the simulation relation must also preserve the violation. This is mathematically stated in the first order formula shown here. In words, this means that if L breaks the specification and the states of L and C obey the simulation relation, then C must also break the specification. The theorem provided here essentially summarizes these formulas and all their conditions into one statement. The tool implementing the ideas presented in this work is still a work in progress, but we have obtained positive preliminary results. Note that for all our experiments we use Z3 as a backend SMT solver. Using Z3, we have established small cutoffs for the leader election in a ring and sharded key value store protocols. The key value store protocol here is significantly more complicated than the leader election protocol, as it assumes an unreliable network and it handles message losses, deals with retransmissions, and also has complicated sequence number logic. Despite these complexities, our technique is able to establish a small cutoff via assimilation proof. Besides these protocols, we have also verified the log service protocol, learning switch, and a distributed log service protocol manually. Going forward, we would like to verify the feasibility of our technique on more complicated protocols. Currently, as we have seen, our proposed tool takes the cutoff instance, the sim function, and the two functions omega and tau as inputs, apart from the protocol description itself. We believe that there is significant scope to automatically generate some of these inputs. We would also like to leverage our observation that the cutoff instance is closely related to the possible violations of the specification. We believe that this can be used to synthesize the cutoff instance in an automated manner. To conclude, in this work, we have proposed an approach to significantly automate and mechanize cutoff-based proofs. Our experience is that such proofs can be applied to a large number of distributed protocols, and we hope that this work could pave the way for more widespread application of this proof technique. Here are our references. Kindly take a look at our brief announcement paper and a full version linked in the paper to read further about our work. Thank you.